Hi, my name is Niall Emmart, and today I'll be giving you a talk on fast NTT arithmetic in the Goldilocks finite field. If you have questions, please feel free to email me at nemmart@urid.com. Here we go. Let's start with a quick overview of the talk. We'll cover some of the early papers and the origin of the Goldilocks prime. Then we'll talk about the properties of the Goldilocks prime and the basics. Then we'll cover the standard 64-bit representation, some non-standard representations, and the rotation trick. And then we'll come to the meat of the talk, which is a new GPU-friendly approach and representation. And we'll conclude with some experiments and some thoughts about a hardware implementation. I guess I should say that this is a fairly technical talk, and it's really targeted for people that are already familiar with NTT and perhaps the Goldilocks finite field. For a long time, I've had an interest in finite fields and NTTs. I had done some work with the GNU multiple precision package, and around 2008, 2009, I knew I'd wanted to go back to graduate school to pursue a PhD, and I was looking for an interesting problem to work on. What I decided on was large integer multiplication using the GPU. I wanted to multiply numbers that were sort of thousands to millions of bits in length. My first efforts, I tried to use a 32-bit finite field. GPU is a 32-bit processor, so that sort of made sense. But those efforts didn't work out too well. In general, you just can't multiply very large numbers with a 32-bit finite field. So the next natural thing was to increase the field size to 64 bits. And at that point, I knew I wanted to do entities of size 2 to the 32. And it turns out, as you start searching for primes, the largest prime that fits those requirements is the Goldilocks prime. So I discovered that in 2011, and I built a multiplication library on the GPU. And as part of that work, I started to research, who may have found this prime prior to my work. And it turns out 2 papers earlier than that had covered it. Jerome Salinas published a tech report in 1999 where he described this class of generalized Mersenne primes. And then there was a follow-on paper by Angel and Morales Luna in 2010, which had the specific Goldilocks prime in it. But I think my paper here, this one in 2011, was the first one that actually used it in NTT. Around the same time, around 2011, Gentry's fully homomorphic encryption algorithm had come out, and that's an application that requires million-bit multiplies. So a bunch of people in Worcester Polytech started working on Gentry's algorithm and doing implementations both in software, on the GPU, and in hardware. And that led to a paper with some other folks from WPI, where we built a large integer multiplier in FPGA with a VLSI design. This paper introduced some new ideas, which we'll talk about further in the talk. Okay, so what is the Goldilocks prime? So it turns out it's this number. It's 2 to the 64 minus 2 to the 32 plus 1. And if you write it in hex, it has this really nice pattern where the top word is all ones, and the bottom word is just the number 1. So as I mentioned, it's the largest prime, supporting entities of size 2 to the 32. And what's really nice about this finite field is that it has a very fast modular reduction. Normally, to do a modular reduction, you have to have multiplies in there. For this particular prime, and other primes like it, I guess the whole Salinas family, you can do that typically with just additions and subtractions, and you don't need multiplications. And one final property of the Goldilocks prime is that for small entities up to 64 points, the roots of unities are often powers of 2. Now there are lots of roots you could choose to do your NTT, but if you choose the right ones, then they're all powers of 2. Let's take a look at an example of an 8-point NTT. This is a Cooley-Tukey decimation in time. You have 8 values that flow into this network on the left-hand side, and every one of these sort of places where the arrows intersect along here, this represents additions and subtractions. This next step where you see these W's, these are multiplication by roots of unity. Then another sequence of adds and subtracts, another sequence of multiplications by roots of unity, and then the outputs flow out of here with a final set of adds and subtracts. So what makes the Goldilocks prime really attractive for doing NTTs is that all of these operations are really fast. And that's especially true if the roots of unity are powers of 2, because then they just become shifts. The standard way to represent values in the Goldilocks finite field is just as a big num between 0 and p minus 1. If you want to do addition, it's simple. You just add the two big nums. If the result you get back is greater than p, then you just subtract p. For subtraction, you compute a minus b. If the result is negative, then what you want to do is add p. So these steps will guarantee that if the inputs are between 0 and p minus 1, the output will be between 0 and p minus 1. In general, the expensive step tends to be the finite field multiplication. So here, we're going to take these two 64-bit p values, we're going to multiply them together and get a 128-bit number. And then we want to reduce that 128-bit number modulo p. Now again, here's where the Goldilocks field is really advantageous. It has a couple of special properties, namely that 2 to the 96 mod p is minus 1, and 2 to the 64 mod p is this. It's 2 to the 32 minus 1. So what that means is that if we have a 128-bit result from multiplying these two values in the finite field, we can write it as 2 to the 96 times a plus 2 to the 64 times b plus 2 to the 32 times c plus d, where a, b, c, and d are all 32-bit numbers. And according to the equations above, we can replace this 2 to the 96 with a minus 1, because all of this is modulo p. The 2 to the 64s can become 2 to the 32 minus 1, and then these things are left alone. This is 2 to the 32c plus d. You collect the terms, and what you find is that this x mod p is just 2 to the 32 times this b plus c plus d minus a minus b. So as you can see, the only thing we've done here is additions and subtractions of 32-bit numbers. We haven't done any multiplications. We can also reduce things that are much bigger than 128 bits. When you do that, you'd use the following relation, the fact that 2 to the 192 mod p is 1. So what that means is that you can combine chunks that are 192 bits long. You can just add them up, and you'll get a 192-bit number, and you use the above equations to reduce that mod p, and you'll get a 64-bit number out. All of that is all well and good, but I still think it's worth noting that even doing the standard representation, you have you can potentially have a large number of instructions to actually do the reduction to make sure it's between 0 and p minus 1. So in this paper, the VLSI design of a large number multiplier for homomorphic encryption, they introduced a new idea, which is to use 192-bit redundant representation. So instead of having your finite field values between, being 64 bits between 0 and p minus 1, you let them kind of explode in size up to 192 bits. And the reason that this is attractive is one of the operations that happens a lot in the NTT is you're multiplying by a power of 2 mod p. Now, when you're in the standard representation of 64 bits, that's a shift and then a reduction, sort of like the 128-bit reduction that we saw in the previous slide, which takes a lot of adds and subtracts. But if you go to this redundant representation where it's 192 bits, something really interesting happens. Now we remember that that 2 to the 192 mod p was 1. We had that on the previous slide. So let's look at this in detail. We have a 192-bit number. We multiply it by 2 to the k. Now that's essentially a shift. So we're going to insert k zeros on the right. And these k bits that were at the top now shift out past the edge of the 2 to the 192. But 2 to the 192 is actually 1, so we can just take this value, this YYY value, and we can wrap it around back down here because this is sort of the ones place. So it turns out that a multiplication by 2 to the k mod p is just a rotate left by k bits in this 192-bit representation. So what this means is that you can sort of enter the NTT network in this 192-bit representation, go all the way through the NTT network, and then at the very end of that, convert back to 64 bits before storage. And that's what was done in this VLSI paper. Okay. Unfortunately, though, using 192 bits is a little bit too big on the GPU. What you see is that that's going to be 6 registers in length, and you still have another problem, which is that when you do additions between values that are in this 192-bit representation, you can have carries out. Now in the hardware, it's pretty simple to get rid of those carries and handle them. But on the GPU, you need a whole bunch of other instructions to handle that carry out from the 192nd bit. So the main contribution of this talk is a new idea. Instead of using this very large 192-bit representation, we'll start with a 96-bit representation. And what we're going to do is we're going to break this 96 bits into 4 groups of 24 bits. Okay, 96 is 4 times 24. And we're going to put these 24 bits into a 32-bit register. Okay, and so that means there's 8 bits at the very top of the register. And to start out, we're going to set those all to 0. So you have 24 bits with zeros, 24 bits with zeros, 24 bits with zeros, 24 bits with zeros. Now, if you ever wanted to return to the 96-bit format, essentially what you would do is you would overlap these things. So you get 24 bits from here, 24 bits from here, 24 bits from here, and 24 bits from here. Okay, so what's the advantage of this format? Suppose we have 2 values, 2 finite field values, x0 and x1. Okay, they've both been sampled into these 4 words with 24 bits per sample. So how would we do addition and subtraction? Well, it turns out it's really trivial. To do addition, you just do component-wise addition. So in the least significant word, you have A0 plus A1, and you have B0 plus B1, then C0 plus C1, then D0 plus D1. Now, of course, if A0 and A1 are 24-bit values, you can sort of have a carry into the 25th bit. Okay, but that's fine because we have 8 bits up at the top of this word for carries to accumulate. So what that means is that you can add up a whole bunch of samples before you have to worry about that overflowing. Okay, and likewise, if you want to do subtraction, you just do component-wise subtraction. So you do A0 minus A1, and then B0 minus B1, C0 minus C1, and D0 minus D1. And again, we can have a scenario where A1 is greater than A0, but all that happens is that you get a borrow in this upper 8 bits of carry space. So instead of this having like a 1, it'll have like essentially a minus 1 in the top part. Okay, another thing that happens in the NTTs is that we have to do these multiplications by 2 to the 24, 2 to the 48, and 2 to the 72. So let's look at what happens. Suppose we have a finite field value x0. So it's broken up into its components, a0, b0, c0, and d0. And we want to multiply that by 2 to the 24. So we can think of it as essentially as having a 0 in the least significant word, right? Because remember, there's 24 bits of data in this word, and if we've multiplied by 2 to the 24, essentially all 24 of those bits are 0. And then the a0 value that would have been here, we're going to place that in the next most significant limb all the way up. Now what this does is that this creates a fifth limb, essentially, and remember it's supposed to be a 4-limb representation. So what do we do with this fifth limb? Well, it turns out that you can really think of this as this value right here as 2 to the 96 times d0, right? And we know that 2 to the 96 mod p is just -1. So just like with that 192-bit representation we saw a couple of slides ago, we can wrap that value around from 2 to the 96 back down to the 0. The only difference here, though, is because this is 96 bits long and not 192 bits long, we have to negate this, this value that we bring down. So x0 times 2 to the 24 is simply this. It's minus d0, a0, b0, c0. Okay, likewise, if we want to multiply by 2 to the 48, instead of shifting a single limb, we're now going to shift 2 limbs, right? Because each limb has 24 bits in it, so 2 to the 48 is 2 limbs. And again, this C0 and D0, these stick out. This is this value, this line right here would be 2 to the 96. So this C0 comes down here, and this D0 comes down here. And similarly, if we need to multiply by 2 to the 72, it's just going to be a three-limb shift with negations. In a Cooley-Tukey NTT network, we'll very frequently see equations that look like this. We're going to take an x0 value and we're going to add to it 2 to the 24th times x1. Okay, so let's look at how that operation would work in our sampled format. So let's say our x1 is represented as a1, b1, c1, d1. If we were to multiply this by 2 to the 24, it's essentially a rotation. So this becomes minus d1, a1, b1, c1. And then an addition is just a component-wise addition. So here's what you do. To actually compute x0 plus 2 to the 24 times x1, you simply say a0 minus d1, b0 plus a1, c0 plus b1, d0 plus c1. And that's your answer. So let's return to the 8-point NTT slide that we'd seen earlier. So here, these green circles and the blue circles and the purple circles, these are multiplications by 2 to the 24, 2 to the 48, and 2 to the 72. So in the sampled format that we just saw in the previous slide, these things are just rotations and some subtractions. So now, if we look at the amount of work that it takes to run an 8-point NTT in the sampled format, these first line of additions and subtractions, these are just 4 instructions of 32 instructions of add and subtract per point here. There's 8 points, so that's 32 instructions. The multiplications here are free, they're just rotations. Then this is another 32 instructions. Again, the multiplications are completely free. And then finally, there's another 32 instructions. So what that means is to do an an 8-point NTT in our new sampled format just requires 96 int32 instructions. And that is super duper fast. Okay, now the one caveat though is that after you've finished and you get your results out here, now if you want to store them or move the data around from, like, for example, from one thread to another thread on the GPU, you probably want to reduce it back down to a 64-bit value so that it's as short as possible, because otherwise you're storing a lot more data than you need to, and storing data is generally more expensive than computing. So let's take a look at that. Okay, so now that this sort of idea of how we use this sampled approach is clear, let's take a look on actually doing something on the GPU using it. So, so one of the things that you're going to run into is that after you've gone through the Cooley-Tukey network, you have to resolve the carries and borrows that have accumulated in the upper 8 bits of each of the samples. So here's how you would do that efficiently on the GPU. So your input is, for example, an int4, which has 4 32-bit values: value.x, value.y, value.z, and value.w. The first thing we're going to do is resolve them. So basically, we're going to take the carries that have built up in W, we shift it 24 bits to the right, and then we subtract it from whatever was in X. Then whatever is in X, we shift that 24 bits to the right, and we add that to what's in Y. We do the same for Y and Z, and ultimately we clear out the carry portion of W and add in this other chunk from Z. So now at this point, your X, Y, and Z values, these resolved ones, have 24 bits of data in them, and the carry section at the top of that can be ignored. And your W value has 24 bits of data and 8 bits of assigned value, which is either -1, 0, or 1. And then the next thing we would do is we use the byte permute instruction, which allows us to select bytes from either of the two input words. And we do that to generate a 96-bit result, with this high portion still being whether it's a +1, 0, or -1. And from there, we can use the standard well-known ways to convert from this format HHML back down to modulo P. This is well known. Okay, continuing with our GPU implementation, the next thing that we want to do is implement a 32-point NTT in each thread of the GPU. Okay, and we're going to use Bailey's 4-step method. So the first thing we're going to do is we're going to load our data from memory in this following format. We're going to go across X0 through X7, going across this way, X8 through X15, X24 up to X31, going across this way. Once we've loaded our samples from memory, we need to now convert it from its compressed format in which it's stored, where it's a 64-bit number, out into our sampled format. So now each one of these X values is represented by 4 registers in each GPU thread. So in total, this is taking up 128 registers per thread. Okay, the next thing we do is we're going to run our NTTs going vertically like this. Boom, 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 boom. These are NTT4s. Then we multiply by twiddle factors. And I guess it's worth noting that in this case, omega is a 32nd root of unity. So it's 2 to the 6th. It's a 6-bit shift. And we can do this product inside of our sampled format, our sampled representation, fairly efficiently. There's no need to convert back to a standard. Once that's done, now we can run our NTTs going horizontally. These are NTT8s. We run 4 of them. And then finally, our NTT32 is complete. So now what we do is we do the carry resolution that we saw in the previous slide, and we compress it down to a 64-bit standard representation, and we store that back out to memory. But now the order of the stores is like this. Here's x0 up to x3, x4 up to x7, x8 to 11, x28 to x31, like this. So this turns out to be very efficient on the GPU implementation by using the sampled format. Okay, so now that we have NTT32 as a building block, where it happens in each thread, we're going to build NTT1024, and the way we're going to do that is basically every thread in a warp is going to do an NTT32, and the whole warp together is going to do an NTT1024. And we do this exactly the same way using the 4-step Bailey method that we just used in the previous slide. So let's look at the full experiment here. So the first thing we're going to do is we're going to generate n of these 1024-point entities on the CPU. We're going to generate the data for it. We're going to launch 1 block per SM, and each block is going to have 384 threads, which is 12 warps. So each block can essentially work on 12 1024-point entities simultaneously. Okay, and each warp is going to run the following procedure. It does an atomic add to basically keep a counter of which entity it should work on. It loads the 32 points per thread. Each thread computes a 32-point NTT, just like we saw in the previous slide. The 1024 values that are stored within a warp are transposed through shared memory. That's how the data travels from one thread to another. And note, we want to transpose through shared memory and not with shuffle instructions. You get higher throughput through shared memory. Then the next thing is we do we multiply by the twiddle factors. Then we do another 32-point NTT, just like the previous slide. And finally, we store our values back. It's 32 points per thread. And we overwrite the input data. And what we're going to do is we're going to run this kernel 100 times. And I guess it's important to note that for sufficiently small n, all of this data will reside in L2 rather than going back to global memory. And this is all coded up. The experimental code is available on GitHub at the following URL. Okay, so here are the results from our experiments. So we tried different numbers of entities. This is our n value from the previous slide. The smallest is 1024 up to 6K. And here's the amount of memory that's required for each of these runs. So it goes from 8 megs to 48 megs. And we did this on an RTX 4070 Ti card. So in theory, this card has 48 megs of L2 cache, but the typical way that that's configured is 24 megs is set aside for streaming and 24 megs is set aside for persistent data. Okay, so here are the runtimes for our various runs. And you note this is pretty quick, right? So this is doing 1,000 1024s, and that's run 100 times. So it's essentially 100,000 1024-point entities, and it does it in 2.183 milliseconds. Here, the best time, it turns out, like if you figure out the actual throughput, is at 24 megs. So here we've run 300,000 1024-point NTTs in 4.731 milliseconds, and that turns into roughly 65 million 1024-point NTTs per second as its throughput. Now, it's also important to know whether a computation is compute bound or memory bound. So the next two columns try and tease this out a little bit. So here we have the same kernel, but we don't do the stores out to L2 cache or the transposes through shared memory. It's mostly focusing on the compute. And what you see here is that for this fastest case, this 3072, doing the compute only takes almost the same amount of time as doing the full kernel with the reads and writes. And sort of what that tells us is that this kernel is doing a pretty good job of overlapping reads and writes and compute, and it's almost certainly compute bound. Okay, and this last column here, we implemented the same kernel, but here we don't do any compute really. This is just the data movement portion. And again, this bears out what I was just saying, where if you're just doing the data movement, it takes 2.34 milliseconds to do this this column here, this row of 3K of these things, which is much less than the time it takes to compute it. So as of this column, we're almost certainly compute bound. Okay, now when we look out to 48 megs, this 6,000, here the runtime for the kernel jumps up from somewhere around 5 milliseconds to 12.5 milliseconds. So it's 2.5 times longer, almost 3 times longer in terms of runtime, for twice as much data. And here what we see is that the compute only is 10. So this is kind of what you'd expect, right? This is essentially double this, but the runtime is much longer. And the reason is that we've really shifted from being compute bound to being memory bound at this point. And the likely cause of that is because we're falling out of the L2 cache. And many of the read requests are having to go to global memory. Now, I want to point out one or two things in this table that I haven't quite had time to analyze that strike me as strange. And I'm not really sure what the cause is, but I'm pretty sure that the software is coded correctly. So this is not showing these times as like some bug in the software. These times are really an artifact of the GPU in some way. But here we see in this column, this is the runtime where we do compute and I/O. And this number here is only the I/O portion. You would almost expect this to be lower than this, no matter what. And here we see that it's slightly larger. And again, in this column over here, this row over here, here the total runtime is 9011, but just doing the compute by itself without doing the memory stuff is 9045. So again, you would think that this number should always be smaller than this number. I don't really know what's going on here. If anybody ever takes a look at the code and figures out and has an aha moment and knows what's going on, I'd love to hear about it. Okay, carrying on. Okay, so the last couple of slides, I want to talk about what you might be able to do in a hardware implementation rather than on the GPU. So again, you could start with like a 96-point number like this, but instead of breaking it into 4 32-bit values, you could break it into 16 9-bit values. And the way you would do that is you would have 6 bits of data in here, and then 3 bits of carry space. So this would be a 9-bit value, and there would be 16 of these things going all the way out. Now, 3 bits of carry space isn't a lot. So what you have to do is every time you do an addition, you have to resolve the carries, okay? But that turns out to be pretty straightforward in hardware. And here's how you could think about it. Suppose you have 2 values. So you have an x0 value and an x1 value, and they're represented as 6 bits of data. The data portion will be this BBB, and 3 bits of carry. That's this AAA. Here it's CCC is the carry, and DDD is the data. Here it's FFFF is the data, EE is the carry, HHHH is the data, and GG is the carry. So what we do is we add the 2 data pieces. This is the FFFF plus the HHHH. And for the carry, what we're going to do is we're going to shift it down. We're going to shift it over to the next word here. So then we do an addition. This is the BBB plus DDD. This is the data from above. And we add the 2 carries of EE and GG, and we stick them in this next column. So we're always taking the carries and putting them in the next column. So here's the AA plus CC. Those go over here. Now note, on the top column, we have some carries. We have an XX and a YY. Since there is no next column, these we have to wrap around back to here. And this is going to be minus extend of x plus y. And in this way, you could support a 32-point NTT entirely in this format, right? Without ever leaving this format. And that, I think, would be extremely efficient to do in something like an FPGA. Yeah, okay. I think that's about it for the hardware portion. I guess I showed an addition here. A subtraction would just obviously be all of these pluses turn to minuses and all these minuses turn to pluses. Okay, well, thank you for watching my talk. You made it all the way to the end. If you have any questions, please feel free to email me. Again, my email address is nemmart@urid.com. Thanks, everyone. Bye-bye.